Hey everybody, welcome. Ready for test 3?
This video is going to show you your third test. Your first test was extrema. Your second test was the first derivative test, and this is your concavity and points of inflection test. Before we do more with the concavity test though, I have to make sure you're 100% good on concavity because I think there's still some moments wherever you're not 100% sure of yourself. So I'm going to do really quick examples here of a table, finding rates of change, and how that looks on a graph, just to make it a little more clear the connection between a graph, its rate of change, and concavity. So let's say I have a table here. Jot these tables and graphs down. They don't take long. And T can represent time in years. S can be salary. We can pretend someday I'll make this much money, right? And I want to find the rates of change over time. Now, because the rate of change is not constant, it's not like I can find one slope for the whole thing. The rates of change are going to change. So for each ordered pair set, I'm going to get a different rate of change here. So I'll just show you, for example, what you would do here. Whoops. So y2 minus y1 over x2 minus x1. This one would be 128 minus 72 over 20 minus 10, for example. So that's how we're going to get our rates of change. You can see my rates of change go from 3.2 all the way up to 18.1. And that makes sense because if you look at your y values, they go from increasing just a tiny bit to increasing more. And look at this huge jump from 30 to 40 years. So I'm going to go ahead and plot these so we can see what's going on. When you look at the graph, you can see that if you were to connect this salary graph, it's clearly going to be concave up, which is good for the person who's working right here. So the connection to make is if the rates of change are increasing, the original function f, we're not going to say it, we're going to say the function f that we're thinking about is concave up. And that's going to be a huge relationship you need to know basically for the rest of the year. And since you're in calculus, you know a fancy new word for rate of change, which is derivative. So if the derivative, which are the successive rates of change, are increasing, the function is concave up. Let's do this one here. I'm going to find rates of change again. And T can be time, D can be distance. Let's say we're on a bike ride and these are hours and how many miles we've biked, for example. That might be unrealistic, but you can change the units to make it realistic. Anyway, we're finding our rates of change like this. So for each ordered pair set, first this, then this, then this, for example. I'll write those down in a moment. In this case, over time, the person's traveling less and less every hour, which makes sense because you're going to get tired on a bike ride. Our rates of change are decreasing, and our fancy calculus word for rate of change is derivative. So our derivatives are decreasing, and I'm going to go ahead and plot this. Go plot it as well on your paper, and we'll see what the graph looks like. The curving isn't quite so obvious, but if you were to connect, you can see a big jump in y values and then a smaller and smaller jump in y values. Our graph is concave down, so f is concave down. So if the derivative, the rate of change, is decreasing, the function's concave up. And again, if the derivative was increasing, the function's concave down. So make sure you have all this plotted. We're going to do a 4-square visual to help cement these ideas even more. On your paper, draw these 4 possible combinations of increase, decrease, concave up, concave down for a function. And this should take up most of the paper, just break it up into 4 pieces. So I just want to connect f, f prime, and f double prime, because so far we've been talking about a function and its derivative. Now we're throwing the second derivative into the mix, which makes it easy to confuse increase, decrease, positive, negative. So you want to be very careful. The more visuals, the better, I think, to help cement these ideas. So in this case, we have a function that's clearly increasing, and it's clearly concave up. F is clearly concave up. So if we look at the function f, because the function's increasing, if you picture tangent lines, which are the derivatives, they all have positive slopes. The function is increasing, meaning the derivative is positive slopes. Now, if we also look, remember, we're moving from left to right, just like we read a book. Moving from left to right, the slopes are getting larger, meaning the derivative, which is a slope, is increasing. The slopes are increasing. They're getting steeper. The function's steeper. The lines are getting steeper. So the derivative is increasing. Now remember, if a function is increasing, its derivative is positive. So if a function is increasing, its derivative, which in this case would be the second derivative, is positive. A second derivative being positive will mean the function's concave up, which we can see from the graph. The function's obviously concave up. Let's still take an increasing function, but now make it concave down. So let's picture slopes here. All these slopes are still positive, meaning the derivative is still positive here. However, as we move from left to right, the slopes are getting less steep. The lines are getting less steep, so the slopes are decreasing. The slopes are the derivatives. The derivative's decreasing. If a function is decreasing, its derivative is negative. So the second derivative is negative, our function's concave down. That's a connection we're going to make. Here the function's decreasing. Slopes are all negative, so the derivative's negative. The slopes, this one's the hardest one for people, the slopes are actually increasing because they're becoming less negative. So the derivative or the slopes are increasing. If a function is increasing, its derivative is positive. So the second derivative is positive. We have a concave up function. Last one, a function is decreasing. So all these slopes are negative. So the derivative is negative. The slopes are decreasing. They're getting more negative. If a function, f prime, is decreasing, its derivative, f double prime, is negative. If f double prime is negative, the function is concave down. We'll go through this whole scenario again in class with spaghetti so you can see the visual even better. So make sure you have that written down. Couple more visuals coming at you here. Here's a little memory tool for you. If the second derivative is positive, the original function f is concave up. Concave up looks like a cup. Concave up faces up. If a second derivative is positive, so because it's second derivative, I'm going to draw two positive signs. You can think of like a smiley face. Woo! Second derivative positive, concave up. If the second derivative is negative, the original function is concave down. Concave down looks like a frown. So because the second derivative is negative, I'll draw two negative signs for the second derivative. Look at that frown. That's how you can remember that. Okay, so here's a definition for you. Point of inflection. That's a big calculus word. A point of inflection is a point on the original graph where the second derivative changes sign there. Now the function has to be continuous for there to be a point of inflection, in this case here. So think about it. If a second derivative has to change sign, that means the second derivative needs to go from positive to negative or from negative to positive, meaning the second derivative has to hit 0 at some point or does not exist. There are 4 possibilities for a point of inflection. So here are all the points of inflection. So draw these little graphs and label them here. Then make sure you're actually paying attention to what you're writing down. Don't just like really quickly scribble this down just to have it, or else you won't remember any of this. Try to remember the connections we made. Second derivative is positive, concave up. Second derivative is negative, concave down. The second derivative goes from being positive to negative, so I have my point of inflection. But remember what we can say, if a second derivative is positive, the function's increasing. I'm sorry, the derivative is increasing. If a second derivative is negative, the derivative is decreasing. Here we have concave up, so second derivative is positive. We have concave down, second derivative is negative. The derivative is increasing, because if the derivative is increasing, the second derivative is positive. Here the derivative is decreasing, so the second derivative is negative. In this case, the derivative would be 0, so the second derivative would be 0. In this case, we have a vertical tangent line, so the derivative doesn't exist. And if the derivative doesn't exist, then the second derivative also can't exist there. So that's what I mean by the second derivative has to be 0 or doesn't exist. Okay, here we have concave down to concave up. The derivative is decreasing. The slopes are getting more negative. The derivative is increasing. The slopes are getting less negative. Point of inflection. Here the second derivative doesn't exist. Here the second derivative is 0. Okay, concave down, the derivative is decreasing. Concave up, the derivative is increasing. Point of inflection. The line that you need to remember is a point of inflection is where the second derivative changes sign, positive to negative or negative to positive, or where the first derivative goes from increase to decrease or decrease to increase. Now, if a second derivative goes from increase to decrease or decrease to increase, the derivative has some kind of extrema going on there. All right, let's try an example here. Now, we have a lot of tables going on here. You have to keep the table straight. We did an extrema table, which is where we set the derivative equal to 0 or dne. And it was also, once we had those critical numbers, we plugged them into the original function, and you just looked at the y values. The extrema test, where we found absolute max and mins on a closed interval, you had your first derivative test, where we found relative max and min locations, no y values here, just the locations, on an open interval. And we had these intervals, we broke it up into pieces based on the critical numbers. There's no endpoints here. We picked test values and we plugged them into the derivative. And then we saw is the function increasing or decreasing. So this was for extrema. Now we're going to do a very, very similar table to the first deriv test. Whoop, right here. All right, so we want to find points of inflection. And we want to find regions of concave up and concave down. So to find points of inflection, let's start by finding concave up and concave down. So concave up means the second derivative is positive. Concave down means the second derivative is negative. So let's just find where the second derivative changes sign and is positive or negative. So POY, second derivative changes sign. So let's find where the second derivative is 0 or dne to start with. This is similar to finding where the first derivative was 0 or dne. So let's find the first derivative first. 4x cubed plus 18x squared plus 24x plus 8. Now we want to know where the second derivative is 0 or dne. So let's keep going here. Plus 36x plus 24. All right, I want to know whether this function is 0 or dne. Now, we have a polynomial here. So a polynomial never does not exist. The polynomial exists everywhere. So we can only find where this polynomial equals 0. Now, I don't feel like factoring with a 12 there, so let's take a 12 out and make our factoring life way easier. 12 is irrelevant. It only matters if we were graphing it. We're not graphing the function. Okay, 2 times 1 multiply to 2 and add to 3. So I have -2 and -1. Now, these are possible. Make sure you label this. These are possible points of inflection. These are not critical numbers, because a critical number would be where my derivative was 0 or does not exist. That's for extrema. I want critical numbers. I'm sorry, oh my God. I want points of inflection. So I want to know where the second derivative is 0 or dne. So I have possible points of inflection here. Now I'm going to break up my number line using my possible points of inflection. So I have an interval negative infinity to -2. There's a possible POI here, -2 to -1. Another possible POI here, and -1 to infinity. So just like for the first derivative test, I'm going to get test points, but I'm plugging them into the second derivative to see where the second derivative changes sign. Very similar, but the main difference is we plug in the second derivative. So I'm going to pick, let's say, -3, -1.5, and let's do 0. Plugging in, I'm showing my work plugging in. I don't need a value here. I just need to know positive or negative. So a positive times a negative times a negative will be positive. A positive times a positive times a negative will be negative. Then a positive times a positive times a positive is positive. Okay, second derivative is positive, means f is concave up. Second derivative is negative, means f is concave down. Second derivative is positive, means f is concave up. And if we look at a graph, we can see negative infinity to -2, I'm concave up. -2 to -1, f is in fact concave down. -1 to infinity, f is concave up. That's just confirming what we just found. So make sure this is all written down, and then quickly let's just do our conclusion. Your justification, just make sure you say what is happening, so what is going on with f, where it's happening, the points or the intervals, and why, using the second derivative to justify. So copy this down and we'll practice in class. Bye!